All right. So the idea of acceleration should be review because you talked about that in Science 10. Okay, so quickly then, acceleration is any change in velocity over time. Okay, if our velocity changes, whether it increases or decreases, the object is accelerating. Okay, that would also include if the magnitude of the velocity stays the same, but the object changes direction. Okay, that is still also an acceleration because velocity is a vector quantity, and any change in any part of velocity still counts as an acceleration, right? To kind of further explain that, if I want to turn, I have to exert a force in the direction I'm going or that I want to turn in. That changes my velocity. I have to be pushed that way, and any push or pull causes an acceleration. Okay, everyone kind of follow me on that? That's why in the wintertime, if you're heading towards a corner and it's icy, you can turn the wheel all you want, but you don't turn. Ever had that experience? It's frightening, right? So and every year it's on Canada's Worst Driver, the icy corner, because what does everybody do? Crank the wheel and slam on the brakes. The two things that result in you continuing to go straight. Okay, the best thing to do is back off the gas and not turn so sharp. You will actually turn better because the forces will work to help accelerate you. That is, to change the direction the car travels, not necessarily slow the car down. Right. The other good idea would be if it's icy, don't go so freaking fast. Okay. Also, but I know you're young and speed is fun and whatever. Okay. Yeah. All right. So. Understand what acceleration motion is. Well, we know that. Okay, we know that from Science 10. Any change in velocity is an acceleration. Okay, any change in speed is also an acceleration. Okay, but acceleration, is it vector or scalar? It's vector. Okay, any change in velocity is acceleration. Acceleration can have direction, right? For example, acceleration due to gravity is always down, right? Okay, learn the relationship between change in velocity, distance, time, and acceleration. This is going to be all of the new formulas. Okay, we're going to use last year's formula, but we're going to add like 4 more to it. Okay, there are 4 more acceleration formulas to use here. Right, and then obviously be able to use those to solve problems. Right, this cartoon here is kind of leading towards what we're going to be doing next week, which is projectile motion. Okay, which is you project something into the air and watch what happens. Generally, the same thing happens all the time. It makes an arc and eventually comes back to Earth because gravity pulls it there. All right, so the definition of acceleration, whenever the velocity of an object is changing, the object is accelerating. Okay, average acceleration or uniform acceleration is probably best exemplified by a plane at takeoff. Okay, a car accelerating away from a stoplight is not a good example of uniform acceleration because the rate of acceleration of a car changes as you change what? Gears. Okay, as you change gears in a car, your rate of acceleration changes. I'd have to look. I haven't seen what the acceleration curve of an electric car looks like, but I would still assume it would be. Yeah, because you don't have the gaps where you're changing gears. Right. CVT, though, you still do notice that there's a change in the rate of acceleration. Even in a CVT, when you floor it, you don't, like if you're already at highway speed, the acceleration is not like when you're stopped. Right. With electric motors, it might be a bit different. I haven't looked. I'd have to check that. It's not chopped, but it still flattens. Right, but what I'm saying is, even for an electric car, there comes a point where it can't accelerate anymore as it reaches its top speed, right? So most cars have an acceleration curve that does that. At first, they accelerate very quickly, but as they get closer to their top speed, air resistance becomes more of a factor. They're not powerful enough to continue that rate of acceleration. Okay? Whereas a plane going down the runway is more capable of doing that simply because, again, no gears, and it's more streamlined, designed to do that. Right? I mean, a plane's still going to end up doing this eventually, but at least down the runway, its line is a bit more linear. All right, this is the formula you learned last year. Black is not a good color to use there. Okay, that's formula you learned last year. Change in velocity over change in time equals acceleration. This is also the slope of a line on what kind of graph? It has velocity and time. Oh, no, you're right. That's the formula. I'm saying, what graph would this have come from that from? Position versus time or velocity versus time? Velocity versus time, in that it has velocity and time in formula. Sorry, I thought I was really lobbing that one out there. But, okay. All right. So if we're using this formula here, okay, we've got A equals VF minus VI over T. Sometimes it's written like this: delta V over delta T, means the same thing, right? And we said before that that's really just a manipulation of Y equals mx plus b. Okay. On a velocity versus time graph, where this side's in meters per second and this side's in seconds, Y is a velocity, B is a velocity. Okay, so this would be Y, that looks like an X, Y minus B, okay, and this would be X, right? So that's where we get that formula from. Okay, is that ringing a bell for everybody? And we kind of talked about that when we talked about graphs. All right, so if I have this plane here and it accelerates from rest, okay, and from rest is one of the terms we have to be familiar with because it's often used as opposed to saying the initial velocity of the thing was 0. It just says from rest. Okay, we have to recognize that if something starts from rest, VI is 0. If it comes to rest, VF is 0. All right, so anytime you see rest, it means 0. It's stopping, okay, but you have to determine whether it's initial or final based on the context of the question. All right, in this case, we're starting from rest, so VI is 0. Okay, the plane accelerates down the runway for 29 seconds, attaining a velocity of positive 72.2 meters per second, where the plus sign indicates to the right. Okay, determine the average acceleration of the plane. All right, so in this question here, I have VI, and it's 0 meters per second. I have VF, and it's 72.2 meters per second. And I have the time, 29 seconds. I'm being asked to calculate acceleration. Can I use my good old Science 10 acceleration formula? Okay, I can plug in for that. So A equals VF minus VI over T. So that'll be 72.2 minus 0 over 29 seconds. All right, so we're looking at an average acceleration of 2.5 meters per second squared. And meters per second squared means meters per second, right? It's the rate of change of velocity. It doesn't mean any of the numbers are squared, okay? It just means that it's meters per second per second. There's 2 seconds there, okay? All right, is that ringing a bell from last year? Everybody's okay with that formula? All right, so that's what we just did there. Let's get past that. Okay, these are our other formulas that we're going to learn how to use. Okay, we've got these two here, which are kind of related to each other. One deals with how far you go given the initial velocity, acceleration, and time. One gives you how far you go based on the final velocity, acceleration, and time. You can see here, the one big difference is that VI times T gives us an addition operation, whereas VF gives us a subtraction operation. Those both basically come from your velocity versus time graph. So if I had a velocity versus time graph that looked like this, okay, where this was meters per second and this was seconds, how would I calculate the displacement of that object using that graph? How do we get displacement from a velocity time graph? Right. We use the shapes. We find the area under the line because essentially what we're doing is taking average velocity times time. Well, if I take initial velocity times time, that essentially calculates the area of this rectangle because this would be VI and the base would be time. Okay, so that's calculating the area of that rectangle, and then the 1/2 AT squared is just another way of finding the area of this triangle without using like base times height over 2. All right, everyone kind of follow me there? Whereas if I'm dealing with this formula, instead of using this, it calculates based on VF. So it says, all right, VF times T calculates this whole rectangle and then subtracts the triangle away. Okay, like this triangle here. Okay, it subtracts this triangle here and leaves me with that area instead. Everybody all right with that? Okay, so they both work in kind of the same way. They're using the basis of the graph in order to get us displacement. Okay, VF squared equals VI squared plus 2AD, another formula. The nice thing about that one, doesn't require you to have what? It's in basically every other formula we've ever used. No time. Okay, you don't need time for this one. This is based solely on acceleration, displacement, and the two velocities. All right, and then our last one, okay, we don't use this one as much because it's a bit of an approximation, but really what it is this, D equals V times T, V average times T. But one of the things I've always told you is you can't use V equals D over T for an accelerating object because it uses the average velocity, not initial and final. Well, this one kind of circumvents that a little bit and finds the average velocity by going final velocity plus initial velocity divided by 2. Okay, which, as long as the acceleration is uniform, is true, okay, multiplied by time to get us displacement. All right, it works. We don't use it all that often. Okay. We do use this one a lot, okay, especially when we get to projectile motion. We'll use that one a lot. Okay, questions there? So those are our new ones. They're all on your formula sheet. We're going to go over some examples basically of each type so that you can see how these formulas work, how they manipulate, okay, things like that. All right, so we're going to go over those examples here. Okay, so first example. I have a hybrid car with an initial velocity of 10 meters per second. All right, what did they just give me? Which variable? VI, right? Okay, so VI is 10 meters per second, and they said it was east. All right, it accelerates at 3 meters per second squared east. What did they just give me there? Acceleration. Okay, and it was also east. How long will it take? What are they asking me to find? Time. To reach a velocity of 25 meters per second east. All right, everything's east, so does direction matter here for me? Everything's east, and time can't have a direction, so as long as I know it's all east, everything's going to be positive. Everybody okay with that? All right. So what formula do I have that has those 4 things in it? This is where writing down your givens becomes important. Okay, we have 5 acceleration formulas to choose from. I've got to write down my givens so I know which one to use. Okay, which formula should I use given these givens? Right, okay, going to use the old one from Science 10. Acceleration equals final velocity minus initial velocity over time. Those are the things I have. But I'm looking for time. So I've got to manipulate here. So how do I get time by itself? Do I want it to stay on the bottom or do I want it on the top? Where does it make more sense for it to be? If I want to solve for something, it should be by itself and on the top. Okay, so I'm going to multiply both sides by t. That's my first step. T is going to come over here, so I'm going to have t times a, and then I want t by itself, so I'm going to divide both sides by a. So a comes over here. So my final formula is that time equals the change in velocity divided by acceleration. Now I can plug in my numbers, right? So VF was 25, VI was 10, acceleration was 3, so I've got 15 over 3, so this should take 5.0 seconds. Okay, that'd probably be like a 4-mark question. I would give you 1 mark for the givens, I'd give you 1 mark for choosing the correct formula, 1 mark for your manipulation of the formula, and 1 mark for your final answer. Okay, everybody all right with that one? Okay. Try those 2. They both involve using that formula. One thing to watch in number 2. You have to do a unit conversion. Can't use kilometers per hour and meters per second squared together. So for number 1 here, it's just like the example we just did. Okay, we have a motorcycle whose initial velocity is 6 meters per second. Okay, and that's east, but everything in the question is east, so I'm not even going to bother to write it. Okay, it accelerates at 4 meters per second squared, and it reaches a final velocity of 36 meters per second. Okay, and we're looking for how long that takes, right? So again, A equals VF minus VI over T, and we're manipulating for T. So we multiply both sides by T, then we divide both sides by A, and we've got our formula. T will equal the final velocity, 36, minus the initial velocity, 6, over 4, okay? And so we've got 30 over 4, okay, which is what, 7.5? 7.5 seconds. Okay, how are we doing on number 2? Is the kilometers per hour thing throwing us? Okay, how do I convert kilometers per hour to meters per second? I divide by 3.6. Okay, we talked about that before. It's a compound conversion. Okay, but you're probably just as well to remember that just divide by 3.6 and you've got meters per second from kilometers per hour. Then when you're all done, multiply by 3.6 and you'll be back to kilometers per hour again. Okay, so I'll give you a couple minutes on that and then we'll do it together here. Okay, so for question number 2, first thing we have to do is convert kilometers per hour to meters per second. So 20 divided by 3.6 comes out to 5.5, essentially repeating. Okay, then we have our acceleration is 1.5 meters per second squared. They're all the same direction. They're all north. Okay, the time is 9.3 seconds. So we're looking for VF. So A equals VF minus VI over T. I need to get VF by itself, so I move what's not attached to VF first. That's T. Okay, multiply both sides by T. T comes over here, then I'm going to add VI, which should make sense. T times A is equal to the change in velocity. So if I take the change in velocity and add what I was started with, I should end up what I finished with. Okay, so VI plus T times A will equal VF. All right, so that'll be our 5.5 repeating, okay, plus T times A, which was 9.3 times 1.5. All right, so we got our, so 20, not 220 divided by 3.6 gives me that. All right, I'm just going to use that so I keep all the decimals, plus 9.3 times 1.5. All right, should give me that. Now I'm going to convert that back to kilometers per hour. So I multiply by 3.6 and I get 70 kilometers per hour north. Okay, got to have the north on there because they gave me that at the start of the question. Okay, we're going to be working on the rest of the formulas tomorrow. Okay, lab on Thursday. Remember that your map activities are due tomorrow. All right, so make sure you sit down with your group today and check and make sure all the parts are done. All right, you don't want to hand it in and have parts missing.